Yeah, so last time we were looking at Green's functions and propagators. So let's quickly go through that. And then today we're going to move on to the Dirac equation. So Green's functions and or propagators are the mathematical representation of how a source are used to help us understand how a source modifies a field at some different space-time point. So we saw some examples of that. For example, for static electric fields, we saw that the Green's function for the massless wave equation reproduces the Coulomb potential. And therefore the standard force law. So this really helps to illustrate the importance of Green's functions. And then we looked at the general Green's function for the massless wave equation and emphasized the point that because you have these two poles, and we use Cauchy's theorem to evaluate the Green's functions, then different choices for contours will give you different types of propagators. So this was the example. This contour was the one that gives you the what's called the retarded propagator, which in the end we can write it as essentially the Coulomb potential times a delta function. And this one's called the retarded one because the signal originates in the past, meaning on the backwards light cone of the point at which the signal is received. And it's on the light cone because here we're talking about the massless wave equation. If we added a mass term, then it will be inside the backward light cone. Then doing the contour integral with the contour below both of the poles, you get the sort of time symmetric opposite solution, which is the advanced propagator. And then doing the other two possibilities gives you the Feynman propagator. So we'll finish this section by talking about scattering, which kind of also emphasizes a bit more the interpretation of the Green's function. So mathematically, the Green's method for the massless wave equation, or massless and massive wave equation, provided you give appropriate boundary conditions on a Cauchy slice. So, on a three-dimensional appropriate boundary, the solutions will be unique. So a physically quite natural pair of boundary hypersurfaces are the hypersurfaces t equals minus infinity and t equals plus infinity. So in other words, we're looking at the spatial slice either in the far past or in the far future. So both of those will give us a solution to the wave equation if we put some source in the far past or far future. So let's call those things, say if we're talking about Maxwell's equations, let's call these things A initial and A, or A in and A out, or you could also write A initial and A final. So yeah, those words are usually used interchangeably in field theory. The in and out meaning, I mean, the reason we have that terminology is that we're thinking of states coming in from the past and then some interaction happening, which will be due to the source, and then some other states go out at infinity. At this classical level that we're doing it, here we're just talking about the initial and final field configuration, but in quantum field theory, these will actually be states, for example, configurations of particles. So the so we'll get two solutions this way, which are actually equivalent because we have a symmetry in this situation. And if we just compare the out with the in, then they are, they're given in terms of the source being propagated by this propagator that we introduced earlier. And all I really wanted to mention here is that in quantum field theory, we will normally sort of write this as this equation in the box, where we're thinking now in terms of states in the future arising from states in the past due to interactions, but because eventually in the quantum theory we'll be having an actual Hilbert space of states. So a state will be labeled by a vector. The out states are given by some matrix multiplied by the in states. And that matrix is usually called the S matrix, or scattering matrix of the theory. So part of the one of the main goals of quantum field theory is to try and understand what the S matrix is for a given, say, for example, Lagrangian field theory. Yeah, this is more or less just saying, I mean, this slide is more or less saying what I've just said. So I'm now going to switch to a different topic, which is the Dirac equation. So this will be the last of the relativistic wave equations that we're going to meet. So far we've had the Klein-Gordon equation and Maxwell's equations. We're now going to spend today and the next lecture. By the way, the next lecture will probably take place, is going to take place tomorrow as opposed to Thursday this week. So there's a flip between Wednesday and Thursday today, this week. So the Dirac equation, so I'll begin with some motivation. So the Schrodinger equation, if you remember, is first order in the time derivatives or Hamiltonian, but non-relativistic. Klein-Gordon equation is second order in time derivatives, and therefore also of the Hamiltonian, but relativistic. And so one of the things Dirac was interested in, is there a relativistic equation which is first order in the Hamiltonian? And the answer to that is yes, and that equation is called the Dirac equation. And the Dirac equation is extremely important because it's used to describe fermions in relativistic environments, and is therefore a key ingredient of the standard model of particle physics. So let's sort of follow our noses, follow Dirac's nose, if you like, how he had derived the Dirac equation. So if we had such an equation, which is first order in the Hamiltonian, then it will have to be of this form. It would have to be the Hamiltonian operator acting on the field has to be linear in the three momenta. So there'll be some coefficients, alpha 1, alpha 2, alpha 3. And then it could also be linear in the mass, because at rest, the Hamiltonian in an eigenstate should give you the mass of a particle, for example. But then we have a constraint, which is that the square of the Hamiltonian, which is an eigenstate, would be E squared. That has to be equal to P squared plus M squared. So whatever those coefficients alpha and beta are, they have to satisfy this equation here. The product of alpha dot P plus beta M with itself has to be P squared plus M squared. So in that product, there are 9 terms which are quadratic in the momentum, because you've got alpha dot P times alpha dot P. But those 9 terms here, these 9 terms in the box have to add up to P1 squared plus P2 squared plus P3 squared. So for example, let's look at the terms involving P1 and which are proportional to P1 and P2. Oh, so you could have this term, but you can also have this term. And the sum of these has to add up to 0, because on the right-hand side of the squared equation, there's no P1 times P2. So in other words, alpha 1 and alpha 2 have to anti-commute with each other. Similarly, we get this equation here, which tells us that alpha 1 squared should be the identity. I hope I made that relatively clear, but please ask if it was confusing in any way. Okay. So if you work out all of the different constraints that the requirement of the equation is relativistic are, then they're given here, which I'm going to now leave as an exercise, which is straightforward. So what this means, and this is where sometimes one can get some confusion, is that you see you have here anti-commutators appearing and obeying non-trivial identities. And so it means that the alpha I and the beta I cannot be complex numbers, but they have to be operators of some kind. I mean, operators which are beyond C number operators. And Dirac's idea was that they'd be promoted to matrices. This turned out to be an extremely powerful leap of faith to make. So this algebra is called well, I'll call it the Dirac algebra. And it turns out that it has representations. The lowest dimensional representation is given by 4 by 4 matrices. The matrices themselves in a given representation are not unique, so one has to work with sort of specific representations. One example, which is common in physics literature, is this Dirac-Pauli representation, where the alphas are given by these off-diagonal 4 by 4 matrices whose off-diagonal blocks are the Pauli matrices, and beta is diagonal with entries either +1 or -1. Another representation, which is the one we're going to use mostly, actually, is the Vial representation. But I think in the QED course, you'll probably see the Dirac-Pauli representation a bit more. Anyway, in the Pauli representation, the alphas are block diagonal with the non-zero entries being either plus or minus the Pauli matrices. And in that representation, beta is off diagonal. So just so you start getting used to the Dirac algebra, one can check as an exercise that these matrices actually do what has been claimed. Now, we've got these, you can have different representations. I've just shown you two. Physics itself cannot depend on the choice of representation. If you calculate some observable quantity, it will be independent of the choice of representation. But in order to do calculations, we have to pick a representation. So today we're going to spend quite a bit of time looking at the free particle solutions. Now, the fact that the gamma matrices, sorry, the alpha and beta matrices, we'll introduce the gamma matrices shortly. The fact that these matrices are 4 by 4, it means that, when we go back to the original equation, if you look at the right-hand side, now these alpha and beta are 4 by 4 matrices. So it means that psi itself, the Dirac field, has 4 components. Meaning, you should think of it as a vector with 4 components. And those 4 components, this is natural because the Dirac field transforms in this representation of the Lorentz group, or more precisely the cover of the Lorentz group, which is the representation we studied at the Lie algebra level in a couple of weeks ago. So the Dirac field is the direct sum of the left and right-handed spin 1/2 representations of the Lie algebra of the Lorentz group. And since this representation is 4-dimensional, it's 2 + 2-dimensional, those are the 4 components of the Dirac spinor field. Any questions so far?
So from the observation that the matrices are 4 by 4, and we can conclude that it is more transformed in the half plus half representation. Is it like not? It seems to me not to be very rigorous, because
oh no, I haven't proved it to you, but I will prove it to you.
Oh, all right.
I'm just trying to give a reason why before we see it. Johan, did you have a question?
Yeah, I wanted to ask what exactly is the spin group you talked about in the end?
This is we actually did talk about this, I believe, when we were doing the representation theory of Lorentz and Poincaré. But okay, let me spend a minute on this. So if you recall that SO3 is actually SU2 divided by Z2. Are you happy with that statement? Well,
Yeah,
in fact, SU2, another name for it is the spin group in 3 dimensions. And there's an analog for of these statements when you include boosts as well. So, for example, SO3, 1, there are different ways of writing it. They're all equivalent. It's the same as SL2C, not Z2, but this is also the same thing as what I'm calling spin 3, 1. So it's just the half at the level of the Lie algebra. It's just whether or not you have representations of spin 1/2 or not. So upon exponentiation, any representation that has spin 1/2 becomes a representation of the spin group, not really the Lorentz group. The Lorentz group, by definition, doesn't have half spin representations. But SL2C and spin 3.1 do. SO3.1 only has vector representations. I mean, representations of integer spin. But these things are often confused in the physics literature, but I'm being mathematically rigorous when I make this statement. Any other questions? Okay, I'll go on. So we studied the 1/2 0 plus 0.5 representation previously, and we'll see that it comes back shortly. Now, the way we've written it so far, the Dirac equation, it doesn't look terribly Lorentz covariant. But we can make it Lorentz covariant. So here I've written the equation we started with, where I've substituted I d by dt for h, and similarly for momentum. So if we take this equation and multiply it on the left by beta, then we get the equation below, and we use the fact that, sorry, this is a bit messy. Beta squared is the identity. It's one of the conditions of the Dirac algebra. And then, if we define the following four so-called gamma matrices, so gamma 0 is beta, and gamma I is beta times the alpha i's, then if we make that substitution, the Dirac equation becomes equivalent to the equation in the box. Now, the equation in the box, I mean, that is the Dirac equation, but it's written, I mean, it's simplified in the sense that the matrix indices on the gamma matrices are missing, and so is the vector label on psi, or the spinor, let's say the spinor indices of psi. So if I reinstate those, then we get this equation here. And if I write it out in a bit more detail, we get the equation below, where the terms involving the derivatives are a 4x4 matrix operator. So it's important that we understand what this Dirac, this is the Dirac operator. We have to understand what it looks like. So for instance, the term that involves the time derivatives, so if you go back, you have this first term here is of the form I times gamma 0 multiplied by d by dt. So what we mean by that is you just take gamma 0, and every non-zero entry you put d by dt. And gamma 0 was this matrix beta, which was the matrix was diagonal with entries 1, 1, -1, -1, which means now we replace each of those entries by I times d by dt, and then that's what we get. So just to make sure that we all understand precisely what the Dirac operator is, I'll give you an exercise to explicitly write this 4x4 matrix operator. Now, the Dirac algebra in terms of the gamma matrices is actually given by this nice looking algebra here. You take the anti-commutator of a pair of gamma matrices, and then the answer of that is the Minkowski metric. So these algebras are also discovered by Clifford, so they're called Clifford algebras. I also just noted the hermiticity properties of the gamma matrices. Now, if you, instead of taking the commutator, you take the, sorry, instead of taking the anti-commutator, you take the commutator and put a specific coefficient, I/4, then these matrices, S mu nu, are a set of 6 4x4 matrices. And in fact, they are generators for the Dirac representation, which is this left-handed spin a half plus right-handed spin a half representation that we were talking about. And in particular, in the Vial representation, we get the boosts look like this, and the rotations look like this, which is essentially of the form that we were used to before, maybe with some signs and a factor of I or something. But the important point here is that in the Vial representation, the S mu nus are block diagonal. So they're explicitly written in a basis which is compatible with the fact that the Dirac representation is reducible to left spin a half and right spin a half. Whereas that's not true for the Dirac-Pauli representation or most other representations, although it is true that these S mu nus obey the algebra of the Lorentz group, regardless of which representation you choose. So you don't need to write the S mu nus explicitly in order to verify that the Lie algebra is satisfied. You can just do it using the Dirac algebra or Clifford algebra. So I'm going to pause the video there for a sec. Are there any questions so far? I think this answers your question, Trum.
Yes, it's clear at this point.
Okay, before we break, I wanted to say a few personal words about Dirac. So you can see here the Dirac equation on a plaque. I'm mentioning this just to emphasize two sort of social or points of impact. The Dirac equation is written on the floor of, let me see, I've changed color here. This is in Westminster Abbey, which is a big church in London. The only other physicist that's commemorated there is Isaac Newton. And I'm lucky enough to have been present when this plaque, when the Dirac equation was unveiled there. Now, Dirac was the Lucasian Professor of Mathematics at Cambridge University, which was a post held later by Stephen Hawking and previously by Isaac Newton. Well, in Isaac Newton's case, it was a long time before. Dirac is actually my academic great-great-great-grandfather. And the chain goes as follows. Dirac supervised the PhD thesis of Dennis Sharma. Dennis Sharma, by the way, lived in Trieste for quite some time. Sharma supervised the thesis of Stephen Hawking, and Stephen supervised Gary Gibbons, who supervised Chris Hull, who supervised me. That's how it gets to be my great-great-great-grandfather academically. And he was a regular visitor to ICTP. You might have noticed the Dirac stairway, which leads from the campus up to the park. That was to commemorate the fact that Dirac came here often. Right, so now we're going to take a break and come back in 10 minutes, so at 51, 52. My clock just changed. Okay, let's continue then. So like we did with the scalar field theory, we can derive a conserved current for the Dirac equation. And this will correspond to, for example, if we're talking about the Dirac equation to describe the electrons, this would actually be the electric current, the same current which then later on we will couple that to the electromagnetic field. Sorry, there's a lot of noise. I'm going to go and close the door 1 second. Okay, so in order to derive the conserved current, we have to look at the Hermitian conjugate of the Dirac equation. So if we do that, so we just take the Hermitian conjugate of everything, then we get this equation here. And now the way this is written, it doesn't look like the appropriate, like putting it into the covariant form. We have to take another step because of this gamma zero here. So one defines what's called psi bar, and psi bar is just given by the Hermitian conjugate of psi multiplied by gamma zero on the right. And if you define psi bar, then psi bar does obey a covariant form of the Dirac equation. Now, it's important to note that the way, when you're writing this expression, the way the derivative acts is really, in some sense, from the right, as an operator. So one will often see the conjugate equation written with this left arrow, meaning that the matrix operator acts to the left. Okay, so now that we've got this conjugate equation, we can do the procedure analogous to what we did before. So we'll take the original Dirac equation, the one for psi, and multiply it by the conjugate field psi bar on the left. Similarly, we'll take the conjugate equation and multiply by psi on the right-hand side. Then you add the two together and you see that the mass terms come with opposite sign, so they will cancel out. And we end up with a conservation law. So the current is formed by the thing in brackets in the last but one equation, which is psi bar gamma mu of psi. And if we include the charge, we get the quantity that J mu that deserves to be called the current. And that allows us to introduce the Lagrangian for the Dirac equation, which when we think about it now is a function of psi, psi bar, d mu psi, d mu psi bar. And the current that we just derived is associated to the U1 symmetry, where psi goes to e to the I times the charge e times alpha multiplied by psi. And because, you know, the terms in the Dirac equation involve psi bar and psi, you know, psi bar transforms with the opposite phase. And therefore, we have this U1 symmetry and corresponding Noether current. Now, as we mentioned before, in the Vial representation, the S mu nus are block diagonal, so that the reducibility of the Dirac representation is manifest. So we can write the four components of the Dirac spinners, of a Dirac spinner, as a pair of two component so-called Vial spinners. And the usual notation for that is you write psi, the first two components of psi are called psi left or psi L, and the last two components psi right. So I think it should be obvious now that psi left transforms in the 1/2 0 representation, or left-handed spin 1/2 representation, and psi right transforms in the right-handed spin 1/2 representation. So explicitly, at the Lie algebra level, the transformation of psi left and psi right are given here. And these are exactly the representations that we derived earlier. And so we have the rotations given by angles θ1, θ2, and θ3. And we've got the boosts given by the boost parameters eta1, eta2, and eta3. We're going to use these expressions in a moment when we discuss solutions. Okay, so if I write out the Dirac equation in a form which is appropriate to this block decomposition in terms of the sum of these two-dimensional representations, then we can write it in the following way, in terms of this 4x4 matrix written in terms of 2x2 blocks, or equivalently in terms of these two equations for two component spinners. So you see what the Dirac equation does is it mixes the left and right-handed components of the spinner. And an important observation is that if I consider that m goes to 0 limit, so the massless Dirac equation, then the terms on the right-hand side drop out, and these become two independent equations for the left and the right-handed components. And so what that means is that the mass term in the Dirac equation, or sorry, the mass term in the Dirac Lagrangian is a mixing term between the left and the right-handed components of the spinor. And so as a very simple exercise, you can see that explicitly if you compute this mass term in the Vial basis. Now, we got the Dirac equation by looking at what happens when you square the Dirac operator and require it to be the Klein-Gordon operator, which tells us that the free particle solutions to the equation will also be plane waves, just like the solutions of the Klein-Gordon equation or solutions of the Maxwell equations in Coulomb gauge. So if the particle has momentum p mu and a given mass, then we can write the solution as e to the minus I p mu x mu, where p mu squared is m squared, as usual, and the whole thing is multiplied by a spinor field that depends only on the momentum. So U is a Dirac spinor, which depends only on the momentum for vector and obeys the momentum space Dirac equation. So the way we're going to look at solutions is we'll first simplify our lives and go to the rest frame of the particle. We'll solve the equation in this frame, and then we'll make a general boost, which will give you the solution for arbitrary energy and momentum, because we have Lorentz invariance, so we're allowed to do that. So in this frame, gamma mu p mu is just gamma 0 times m, and gamma 0 times m in the 2 by 2 notation is just 0, 1, 1, 0 times m. But the equation contains the minus m term, so we get minus 1s on the diagonal as well, but everything's proportional to m. So if we just, so that equation, so we just have to solve that this 2 by 2 matrix multiplied by u is 0. So if we separate it into left and right-handed components, that equation just tells us that u left is equal to u right. So that's a nice simplifying feature for of the Dirac equation in the Vial basis in the rest frame. So this is the general solution in the rest frame where u left or equivalently u right, is any two-component spinner. So for convenience, and these type of normalizations that we're using are the sort of convenient normalizations that will come up in quantum field theory. We'll take u left or u right to be the square root of m. Sorry, that's not u left, that's u, that's actually u. So we'll take the four component u to be the square root of m times a four component spinner whose upper two entries are zeta and whose lower two entries are obviously also zeta. And zeta is normalized to be 1. So zeta is that meaning zeta dagger zeta is 1. So we could easily take a basis for this. So we've got this two-dimensional space of solutions now, because u could be any two-component, u left could be any two-component spinner. And so the most convenient choice is just to consider spin up, i.e. that zeta is 1, 0, or spin down, that it's 0, 1. So in other words, the equation has told us that we can only choose 2 out of the 4 components of u, but actually this is precisely what we expect from our representation theory of the Poincare group, because we saw what the Casimir operators were for a massive particle. So a massive particle is characterized in terms of just its mass and its spin. So for spin a half, there's only 2 independent physical states or polarizations. Okay, so that was the solution in the rest frame of the particle. Now let's consider a boost in some direction, and we'll take that direction to be the third direction. So if I take the momentum vector m0, now here I'm just ignoring the 1 and 2 directions because the boost is only happening in one direction, so we end up with a 2 by 2 matrix. Then the infinitesimal transformation is given in the first line there, where or the global transformation is, the exponential of the boost parameter, which by the way is also in particle physics literature often called rapidity. So for those of you that go on to study collider physics, rapidity will be an important variable. Yeah, so we take the exponential of the rapidity times 0, 1, 1, 0, and we get, this is the transformed vector. So in other words, the energy is m times the hyperbolic cosine of the rapidity, and the 3 momentum is given by the hyperbolic sine. So that's the actual boost that we're doing in the geometric basis. We now have to take that particular boost and act on our solution of the Dirac equation in the rest frame. So that's given by this transformation here. So the only difference between the spinor half left-handed and spinor half right-handed is just this minus sign over here. And if you work this out, you can write that as a hyperbolic cosine term and a hyperbolic sine term. Then you can rearrange these in the way that I've done here. So I've, in this last line, written it out more explicitly as a 4x4 diagonal block matrix. And now all we have to do is convert the exponential factors into the energy and momentum of the particle. So for that, we go back to our previous expressions. So E was m times the hyperbolic cosine. Which gives me this formula at the top if I rewrite that as exponentials. And similarly for the momentum. And that means that E plus P is the mass times the exponential, and E minus P is the mass times the exponential, but with the inverse boost. So if I take the square roots of those expressions, I get that the square root of E plus and minus P is the square root of m times the exponentials, but with eta over 2. And putting all of that together, we get this solution here at the bottom. So the upper two components are given by this 2x2 matrix in the square brackets multiplied by zeta, and similarly for the lower ones. You get a slightly different matrix, but very similar one for the lower two components. Now, another thing which is sometimes important in particle physics calculations at high energies is the following. So let's take take zeta to be the 1,0 spinor. So we're just looking at spin up solution. Then U takes this simplified form. And now what I want to do is consider the making the boost very, very large. Well, what that does is it gives the particle a lot of momentum, but because I'm taking it very, very large, it also gives it a lot of energy, but E squared minus P squared still has to remain m squared. But in the absolute large boost limit, it means that the mass is much smaller than the energy or the momentum. So it's the relativistic limit, and effectively the particle becomes massless. And if you do that, then you see that the absolute value of E and P have to be equal in the absolute limit. So the top two components of the spinor drop out. whereas the bottom two components remain and become the square root of twice the energy. And when you do calculations when you do cross-section calculations in, say, QED and QCD, one has to know the normalization, one has to have an appropriate basis in which to do normalized relativistic calculations, and you often see factors of square root of 2 times the energy or square root of 2 times the mass if you're working in the rest frame appearing. Now, similarly, if we started with the spin down state, we'll get a similar result, but it's the upper two components which survive. So you see that in the high energy regime, the two solutions take this very simple form in the Vial representation. And in particular, you see that the left and right-handed components have decoupled. So this is equivalent to taking the massless limit of the Dirac equation, if you like. But we did it with a careful normalization so that the limiting solutions make sense. Now, when we started, where are we? This discussion, we started off by looking at the plane wave with e to the minus I p dot x. And then we ended up with these solutions, 2 independent solutions, but there's also 2 independent solutions with e to the plus I p dot x. And so those ones correspond to the positive energy antiparticle solutions. And again, the same steps that we did will give you 2 sets of such solutions. So in total, the Dirac equation describes the 2 spin states of particle solutions and the 2 spin states of antiparticle solutions. And yeah, in that case, we will eventually arrive at, for example, this boosted solution that you see you have a minus sign out front, reflecting the fact that we are looking at antiparticles. Okay, I guess I can spend a few minutes on the next part. Are there any questions about what we've been through so far? So it's an important practical point is that if I'd have started with another representation for the gamma matrices, the solutions would look different. In particular, this left and right sort of decomposition, depending on the representation, may be harder to disentangle. All right, so we'll finish today by starting a discussion about symmetries of the Dirac equation. So we already saw that the Dirac Lagrangian takes this form and that it has a U1 symmetry. Now, what I want to convince you of now is that there's another symmetry when m is equal to 0. And that's precisely there because in that limit, we've already seen that the left and right handed components of the Dirac field decouple from each other. So in order to make that manifest, we have to introduce another operator, which is called gamma 5. And we'll define it to be the square root of -1 times the product of the 4 gamma matrices. And gamma 5, as the way we've defined it, is Hermitian. It squares to 1, and it anti-commutes with the 4 gamma matrices. And that's actually the reason that it's called gamma 5, because if I wrote down the Dirac algebra for gamma matrices in 5 dimensions, then gamma 5 would be the 5th gamma matrix. That's the reason it's got its name, but that's not the reason that it's important for the Dirac equation in 4 dimensions. The reason it's important in 4 dimensions is that it commutes with the S mu nus, the Lorentz generators in the Dirac representation. And in particular, in the Vial basis, it's just the diagonal matrix whose entries are -1 and +1. Which means that its eigenvalues can be used to distinguish psi left and psi right. So there's a nice exercise, which is we can now define another current by inserting a gamma 5 in between the gamma mu and the psi. And this current, its divergence is non-zero, but given by 2i times m times psi bar gamma 5 psi. Which means that when m is equal to 0, we have another conserved current, which is called the axial current. Sorry, I haven't written that very well. And this J mu 5, the axial current, is the Noether current of a new symmetry that of the type we haven't seen before, in which you multiply the Dirac spinor by the matrix, which is given by the exponential of I times alpha times gamma 5. And often, instead of considering J mu and J mu 5, we often consider their sum and difference, because these are purely left-handed or right-handed currents, and obviously conserved, because J mu and J mu 5 are conserved. Okay. So I'll end with just a whole bunch of exercises, which are the following. The first one, let's consider the Lagrangian for 3 massless left-handed fermions. So the question is, what are the symmetries of this theory? Second question, what happens if you try to give that system a mass? Third one is similar to the first one, except we now want to write the Lagrangian for 3 massless Dirac fermions and explain the symmetries. And then finally, in that system, add appropriate mass terms such that the symmetries are broken to U1 left times U1 right times U2. And these types of symmetries are generically called flavor symmetries, ones that act on fermions in particular. Okay, I think that's a good place to stop for today. Does anyone have questions? We actually covered quite a lot of material today. So it's important to sort of go through it again slowly and absorb it. Okay, so I remind you that we'll have another lecture tomorrow and a tutorial on Thursday. Do I have to set exercises up to a certain point today? Or is it better I do it tomorrow?
I think tomorrow is better.
Okay. All right, we'll see where we are tomorrow. All right, I'll see you then.
See you, Professor. Thank you.
Thank you,
See you.
Professor.
Thank you. Thank you.
Thank you.